we've learned that chiral molecules are optically active, but by looking at the molecule, we cannot determine whether or not that optical rotation will be in the positive direction or in the negative direction. We can't predict whether or not we can call a molecule D or L. So these set of sequence rules, which are established by IUPAC, will allow us to designate a chiral carbon as either being named R or S, depending on the spatial arrangement of the atoms attached to the chiral carbon. The four examples that I've drawn here are all chiral, which means they have a chiral carbon and four different attachments to the central chiral carbon. I've not drawn them as mirror images, but only randomly distributed those groups around the central carbon atom. We'll be able to determine if any of these molecules are the same or if they're enantiomers of each other. The first step is to prioritize the atoms as they're attached to the chiral carbon based on their atomic number. So bromine is going to be our highest priority, then nitrogen, then carbon, and then hydrogen. The next step is to orient the molecule so that the lowest priority group, or atom, that being the hydrogen in this case, is pointed away from you. And that is true for the example that I have created here for us. I've made it a little easier. With the lowest priority group facing away from us, we look at the remaining three groups, the bromine, the nitrogen, and the carbon, and we determine if moving from 1 to 2 to 3 is counterclockwise or clockwise. This is a counterclockwise rotation, and based on these rules, that chiral carbon can be designated as S. Let's move to the other examples and add 1, 2, 3, and 4 to the atoms that are attached here, and then we'll go through and determine the chiral designation. Okay, and the upper right example, again, I've got the hydrogen in the back, which is our second ruler. We want the lowest priority group to be behind us. This looks to be a clockwise rotation from bromine to nitrogen to methyl. So this is R. Going down to the bottom left, again, I've got the lowest priority group away from us, and our chirality is moving from the bromine to the nitrogen to the methyl group. This is counterclockwise, so that is S. And then our final one in the bottom right, we'll go 1, 2, 3. This is clockwise, and that is R. So based on this, we can determine that these two molecules are the same, these two molecules are the same, and they're enantiomers if we relate the R and the S molecule. If you find that the lowest priority group is not behind you, but instead it's in front of you, then you can still go through the same methods as you did before to determine the counterclockwise or clockwise rotation between 1, 2, and 3. But in this case, although we're going counterclockwise, we have to reverse the rules because the lowest priority group is in front. So this counterclockwise rotation becomes R. And we look at the other example, this clockwise rotation becomes S. Another way to think about this is if you were to actually place yourself in a point of perspective where the lowest priority group is pointing away from you, so you'd have to kind of climb inside the video screen here and look at it from the other side, you would determine these to be R and S as we've drawn them. Another part of that rule says that if the hydrogen is not pointing away from you, nor is it pointing towards you, then you need to put your eye in a perspective so that you can see the groups where the lowest priority group is pointing furthest away from you. So if we were to look at this molecule from this direction, which puts that hydrogen away from us, then that would be a counterclockwise rotation, or S designation. The molecule on the right side is a little more complicated. In this case, we'd actually have to put our field of view underneath this molecule. This would be 1, 2, 3, and 4. It's a little complicated. Can you determine that to be an R designation? If you're finding these difficult, I've got a tip for you to try. You can apply this to any molecule that has a chiral carbon. Let's look at the upper left molecule. Using your finger, pen, or pencil, point at the bromine atom. That's the highest priority atom. Whatever you're pointing with, make sure that your finger although it's pointing towards the bromine atom, is parallel to this sigma bond, the CH sigma bond. Right? So maybe your finger is pointing in this direction right here. All right, now take that pointer and bring it towards the number 2. So you're going to come out towards you and to the nitrogen, and now go to the carbon. And now you're going to go in to the carbon and up to the bromine, out to the nitrogen, down to the carbon. And if you look at the direction that your pointer is moving in, that's counterclockwise. Let's try that with the right molecule. Point towards the bromine atom in the direction of the CH sigma bond, or the bond that leads to the lowest priority atom. So your finger should be pointed in this direction. Then, to get to the nitrogen, you're going to have to come towards you and to the right, and then to the carbon, you're going to go down away from you to carbon 3, and then back around to 1, up towards you to the nitrogen, down to the carbon, to the left, to the bromine. And which direction is your pointer moving? That's clockwise in R. For the upper left molecule, you'll notice that we have a chiral carbon, but we have 2 carbons attached to it. So this seems like it would be difficult to prioritize these because the atomic number of a carbon is 12, no matter how you look at it. If the atoms are the same, then we move to the next atom in sequence as we move further away from the chiral carbon. So from this carbon on the left side, the next atom in sequence is a hydrogen. These are hydrogens over here. As we come to this carbon, the next atom in sequence is a carbon. Now we can determine that that's a higher priority group than the carbon on the left side. So this is 1, 2, 3, and our lowest priority group is moving away from this, so this becomes R. The chiral carbon within the molecule on the right side has an attachment to a hydrogen, which is already in back, an oxygen, a carbon, and a carbon. So using the same rules, we could look at what's attached to the carbon. This one's maybe a little bit different. Certainly the oxygen's higher priority than a carbon. But between these 2 carbons, can you determine which one is a higher priority? If you said the one on the left side, you'd be correct. So this is our 1, 2, 3. Hydrogen's already in back, so this makes this molecule have an S chiral carbon. This last rule presents itself as being probably the most complicated rule. It's in place to try to address molecules that contain pi bonds, whereby those double bonds or triple bonds are equivalent to the same number of single bonded atoms. And you can look at the examples here. But 9 times out of 10, we can simply determine that multiple bonded atoms are a higher priority than single bonded atoms. Let's look at our examples and see if we can make sense of that. For the upper right example, this is our chiral carbon here, and we have a hydrogen which is in the back already, and we're going to have attachments to 3 carbons that are here. We have a CH2, a CH2, and a carbon with a double bond attachment. And right off the bat we know that that's going to be the highest priority group right there. Next, when we're comparing these 2 carbons, we need to go to the next atom in sequence. So now we're going to be comparing these 2 carbon atoms. And we can determine a difference now such that this side of the ring is a higher priority because of that pi bond. And so this becomes 2 and 3. And with our hydrogen in back, this counterclockwise rotation becomes S. Let's look at the bottom left molecule. Here we have a chlorine attached, a carbon, and a carbon. Now the hydrogen is in front of us in this case, so don't forget about that. But between these 3 atoms, the chlorine is the highest priority atom. Now don't forget that we're still looking at atoms and not the entire group when considering priority. So even though this has a double bond to the carbon, the chlorine is still the highest priority atom. So that's going to have priority number 1. Our next one is going to be this carbon here, which bears the double bond, followed by this one here. Don't forget, when your lowest priority group is in front of you, you're reversing your R and S rules. So this seemingly clockwise rotation is actually S. For our final example on this page, we have a chiral carbon attached to 3 carbons. Each of them are CH2s, and our hydrogen is coming toward us. So if we go to the next atom in sequence now, we're comparing this carbon to that carbon. And here we've identified a carbon that has a double bond on it. And as such, it's our highest priority atom. For the remaining 2 carbons that we determined which were the same, We moved on to the next one in sequence, and again we have a hard time determining this because a carbon is a carbon. But up here, our next atom in sequence is a hydrogen. Here, our next atom in sequence is another carbon. We can continue going around the ring. So that's our second priority, and our third priority is here. Now, with our 1, 2, and 3 in place, and our lowest priority group is coming toward us, this counterclockwise rotation becomes R. If we assign the lone pair of electrons attached to the nitrogen as the lowest priority group, you might think that the nitrogen appears chiral. However, these molecules interconvert rapidly between each other, and we can't isolate the individual enantiomer. Thus, this molecule is not chiral. Most molecules that contain phosphorus bound to 3 atoms and having 1 lone pair are chiral. These don't flip like the nitrogen molecules do. We can prioritize the remaining groups as 1, 2, and 3. Do you come up with an R configuration here? Maybe if you use the tip that I showed earlier, it might be easy as well. Try pointing your finger towards the highest priority group, that being the ring here, but make sure it's pointing parallel towards that lone pair or away from you here. Now move your pointer to the right and down to the propyl group, and to the left to the methyl group, and up. And which direction is your pointer moving? Clockwise. Sulfurs are treated the same. The lone pair is the lowest priority group. Between the 3 carbons here, this can be a little complicated, but if you go stepwise, you find that this carbon is the highest priority carbon as we moved to the second atom in sequence away from that chiral carbon. So that becomes 1, this becomes 2, and this becomes 3. If you place yourself where you need to be to see the lowest priority group away from you, you might see that this is S configuration, or if you use the trick I showed you, where you take your pointer and put it to the position 1 and then move to 2 and then 3, you'll find that's counterclockwise, and this is S. Take some time and try to determine the configuration of the carbons at each of the chiral atoms designated by the arrows on these 2 structures. I'll start with the left structure, and for the left chiral carbon, this is pretty complicated. We know that our hydrogens can have the lowest priority, and we know that this particular carbon is not the highest, so we're competing between these 2. The answer is not simply to note that this carbon is the higher priority because of the pi bond, because that's incorrect. We need to consider that last rule I suggested, which was the one that stated that multiple bonded atoms are equivalent to the same number of single bonded atoms. So for the sake of determining the chirality, we can say this carbon is singly bound to an oxygen, and a nitrogen, whereas this carbon simply has a single bond to a sulfur. But because this sulfur has a higher atomic number, it wins. And so our highest priority group is in this direction, and this becomes number 2, and this is 3. Although that appears to be clockwise, don't forget the hydrogen is coming toward us, so this indeed is S. For the next chiral carbon, we have an attachment to a hydrogen, a carbon, and a nitrogen. Now this carbon does have a double bond to an oxygen, but remember we're looking at the atoms first. So a nitrogen is the highest priority atom here, so that's 1. My hydrogen will have a 4. Now we're simply considering these 2 carbons, and yes, the one with the double bonded oxygen is the highest priority between them. So it looks like 1, 2, 3 is clockwise, the hydrogen's in front of us, so this is also S. For ibuprofen, our hydrogen again is the lowest priority, and now we have 3 carbons to consider, and the one that is doubly bonded to the oxygen is the highest priority. The one that's double bonded to just carbons is next, and the methyl group is a third. Again, this looks clockwise, but the hydrogen's coming toward us, so again, an S designation.